Today, we're going to continue looking at different kinds of coordinates, and in particular, how we look at how we view these coordinates and make them fit into double and triple integrals. So, rectangular coordinates, which we all know and love, have two distances, x and y. So we have a length and another length. So when we look at dx and dy, those are both distances. So when we multiply them together, we get a length times a length, we get an area. So that's why we have a double integral. dA will be integrating a function over an area. It'll take all the points in the region, evaluate the function, add up all the values of the function. What's different in polar coordinates is that r is a length, but theta is an angle. So with x and y being lengths, dx and dy are lengths. So dA is just dx times dy. Length times length is an area. But dr is a length, and d theta is an angle. So if dr times d theta is not an area. So dr d theta on its own is not area. If I multiply these two things, let's make it stand out. Because d theta is a change in angle. So to make d theta into a length, we multiply by r. So multiplying by r tells us how long that change in the angle is going to be in terms of a length. We look at the arc length of the d theta. So we turn d theta into a length by multiplying by r. We make it an arc length. So here, dA is r times d theta dr. So we need that extra factor of r to turn that angle into an arc length. So multiplying by r turns d theta into an arc length. Now I've got a length times a length, and so that will give us an area. That was a real hand-wavy explanation of why that r is there, but we went over it in detail last time. So the important thing here is that we needed an extra factor to turn our angle into a length. We need this extra factor of r to turn the angle d theta into a length. In polar coordinates, only one of the coordinates is a length, the other coordinate is an angle, so we need an extra factor to turn our angle into an arc length. So that's what's going on here. We need this extra factor to turn the angle d theta into an arc length. That way, when we multiply it by dr, we end up with an area. And that's what we need. Because we want to, what we're trying to do is integrate over a region a function of two variables, dA. This dA represents a small piece of the region R. dA is a small area in the region R. Any questions? So, this is why we want to think about it this way, because now we're going to move up to R3 and we'll have 3 coordinates. To determine a point, we only need one of those coordinates to be a length. So let's look at the 3 kinds of coordinates that we have in R3. We have rectangular coordinates, traditionally x, y, and z. Now here, everything is fine because x, y, and z are all lengths. So here we have a length, another length, and another length. What we're doing is we're putting the z coordinate, the z axis, just the z coordinate right on top of the xy plane. We're just saying how high above the xy plane are we going with these rectangular coordinates. Each of the coordinates represents some length, and so the volume, dv, is just dx, dy, dz. I got a length times a length times a length. That'll give us a volume. A triple integral will be integrating a function dv, where dv is a small volume in the solid w. dv is a small solid volume. I want to make it look the same. Small volume in the region, in the solid W. So it's one dimension higher than the dA. dA is a small piece of a region, so it's a dx times a dy, that's a length, or a dr times a d theta, an r d theta. Words are difficult today. I'm glad I'm recording all this mumbling. So dv needs to be a volume. It's a small cube inside the solid W. We're thinking of the W as being just a bunch of little blocks, rectangular blocks. Just as like we're in the previous case, we're thinking of R as a bunch of little rectangles. So W is just a bunch of little rectangular solids. dV is the volume of one of those solids. So to get dV in a triple integral, I would need 3 lengths, dx, dy, and dz. So that's the same as we had in double integrals, the same as we had in single integrals. Let's go one step further. Most closely related to rectangular and polar is rectangular and cylindrical. So cylindrical coordinates say r, theta, and z. Z is just going to be the height above the point r theta. Z is just the height above the point r theta. So cylindrical coordinates, we're just adding height above polar coordinates. We're just adding a z-axis to polar coordinates. So we locate a point, we can locate a point x, y. Those are the same coordinates that we have in rectangular coordinates for R2. That's just the xy plane. So really what we're doing here, we're adding a z-axis to rectangular coordinates. In R2. We're taking R2 and extending it by adding a z-axis going perpendicular to the xy plane. Same thing happens in cylindrical coordinates. We take the r theta plane, which is just sitting right on top of the xy plane, and we're adding a z-axis coming out perpendicular to it. Now we have a similar problem with our dv. in cylindrical coordinates. R is a length, theta is an angle, and z is also a length. So two of the coordinates represent lengths, and one of the coordinates represents an angle. So to get dv, I need 3 lengths. And we do the same thing. Since this is just another coordinate on top of polar coordinates, we can do the same thing that we did in polar coordinates to turn d theta into a length. So in cylindrical coordinates, dv will be r d theta dr dz. R d theta is now an arc length. Dr is a length. Dz is a length. So I have a length times a length times a length. That's a volume. This r that we've included with the d theta is the same r that we had to add, that we multiplied by to turn d theta into an arc length in polar coordinates. See how same? So the d theta is just sitting there in the r theta plane. We need to turn it into a length, so we multiply by r. So we have the arc length as a factor in dv, the same way we had the arc length as a factor in dA. Any questions? The r in the d theta is the same r that dr would be a piece of. We don't want to use the z from the dz because that's not how the coordinates work. The r is the distance from the origin in the xy plane. So what we want to think about, if we think about r2 in x and y, this point is either x and y in rectangular coordinates, and then z is coming out of the page. So z is up here. There it is. Got to get my camera angle right. So z is this point that's above the point xy. In polar coordinates, it's this, here's theta. It's this r here that turns the d theta into a length. So we can't just use z because that's not, the z is not involved in measuring this distance. So this point is r theta. It's r that turns d theta into a length. Notice z is not involved in turning a small change in theta into an arc length. Any questions? So we're not just picking anything to turn d theta into an arc length. We're specifically using r, because r tells us how far from the origin is the points that tells us where theta is. Any questions? So the reason that I'm going to, we haven't done any problems describing things in cylindrical coordinates and rectangular coordinates. We have done some triple integrals in rectangular coordinates. So we got to figure out how to do triple integrals in cylindrical coordinates. We haven't done that because what I'm trying to do is emphasize how we're thinking about this. Rectangular and cylindrical are very close to just rectangular and polar in R2, because we're just taking however we're measuring the xy plane, however we're describing that, with an x and a y, or an r and a theta. And we're just adding a third dimension on top of that. That is just height. So that's why for R3, rectangular and cylindrical are the easiest for us to adapt to, because we're just taking the set of coordinates that we're familiar with, rectangular and polar in R2, and adding height above the xy plane. or the r theta plane. So let's pause the video here before we look at the next kind of coordinate. In case you're playing along at home, I had length, 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 angle, length. So you can guess spherical coordinates are just going to take one of these lengths and replace it with an angle. And that's all we're going to do. We're going to have a length, an angle, and an angle. We can't go to angle, angle, angle because then there's no distance. That's not specific enough. But if we have one length, we can describe a location in three-dimensional space with two angles. So that's what's coming up next. But let's pause the video here and gather our thoughts.